More preserving Cremona group. Zhijia?
Thank you very much for the introduction and the invitation. So yeah, this is a joint work with Konstantin Loginov when he visited New York. So the main object we're interested in are pretty simple. So throughout the talk, the field will be of characteristic zero. It's not that important in the introduction part, but it's more important in our main result part. But for simplicity, let's just assume every field is characteristic zero, and we consider omega n to be this porous invariant volume form on projective space. Oops. Let's go back. Go back.
But you know some people which Zoom presentations with.
Yeah. Okay. So yeah, this is the volume form we're considering. It's the easiest one you could imagine. The one with logarithm of volume logarithm post and torus invariant. Then we're interested in the group of birational transformation of Pn, which over K, which preserves this volume form. And clearly, this is a subgroup of the Cremona group, as you have all seen in Amon's talk, the group of birational automorphisms Dn over K. So the next few slides will be pretty much already covered by Amon. So here is the famous Noether-Casanova theorem. It says over algebraic closed view, Cremona 2 is generated by PGL3 and the Cremona involution. And this is not true over non-algebraic closed view. For example, K over R, because the base locus of the maps have are all rational points. But over non-algebraic closed view, you can have Galois invariant base locus, which are not rational points. So a similar result of the group of interest to us is was discovered by Usnich in 2006 and proved by Jeremy Blanc in 2013. So they show that over an algebraically closed field, the group BER P2, which is birational automorphism of P2 preserving omega 2, in this case, which is just the symplectic form, is generated by the torus SL2Z, which acting on exponents, and also one special birational map of order 5, given by this on the fine chart. It's called the cluster transformation, since it has some connection to cluster algebra. So, okay, here is a photo of which I found online, which I suspect is the manuscript of Castelnuovo's work, because yeah, I was also suspect. I was about to ask you, Paolo. Maybe you could
because it's written Dear Guido.
Okay.
So it cannot be written. I will assume it's not written by.
Sure, yeah, but I assume the content is about.
Oh, sure.
The work.
That
I'm sure it's not the original work. Sorry, I keep going back to the last one.
I thought you told that it was written by Castelnuovo.
Oh, yeah, I don't think that will be true.
No, it was written by someone else.
Yeah, but I don't read Italian, but I guess the content is word. Okay, yeah, it doesn't matter. So, but all I want to say is, the Cremona group is a very classical project and received a lot of study and attention already in the end of 19th century, at the beginning of 19th century. So, however, as Aman mentioned, despite a lot of recent development, the simplest question of finding an explicit generators for Cremona group is still open in dimension greater or equal than 3. And the group structure of this group was also not known until very recently. So, something which was already known is this result by Hudson and Tan. They show that in dimension greater or equal than 3 over algebraically closed field, the Cremona group is not generated by a rational map of bounded degree. And if the field is uncountable, the Cremona group cannot be generated by countably many birational maps. And then in 2012, Cartan and Lamy proved that the Cremona group in dimension 2 is not simple for any subfield of the complex number, and then generalized to any field by Landru in 2016. Later, there's this work by Blanc, Lamy, and Zimmerman showing Cremona group is not simple for any subfield of C in arbitrary dimension. They construct many maps from Cremona group to Z mod 2. And then I'm sure I'm missing a lot of names and milestones here. I'm not really an expert in Cremona group. But the main result I would like to talk about today is this recent result by Lin and Shinder. They show that the Cremona group is not generated by pseudo-regularizable maps, and as a corollary, they're not simple in many cases. I will define what pseudo-regularizable map in the next slides. But I just want to mention on the positive side, we do know that the Cremona group is generated by Sarkisov link, the classical Sarkisov programs, and there's also the work by Porty, which showing a volume-preserving birational automorphism of Pn. Like the maps in the group we are interested in is also generated by Sarkisov link, but the volume-preserving ones. So here is a definition of pseudo-regularizable map. A birational map is called pseudo-regularizable if it is conjugate to beta by alpha, where beta is any other birational map. Alpha is a birational map from X to other projective variety Y, and beta is an isomorphism in codimension 1. So an easy example is also among already mentioned. If a birational map has finite order, it's pseudo-regularizable, but in fact it's regularizable, meaning we could just remove in codimension the condition that in codimension 1 on beta. It's actually an isomorphism after blow up. And this example of a Cremona evolution is regularized on the Depauw surface of degree 6. Okay, and as a corollary, the Cremona group in dimension 2 and also the volume preserving subgroup is generated by regularizable elements because they are generated by finite order elements. Now here's the theorem by Lin and Shinder on the Cremona group. They show that in each of the following cases, the Cremona group is not generated by pseudo-regularizable elements. And here are the conditions. The dimension, when dimension is greater or equal than 3, K is these fields. I will explain why they need this assumption on the field. And for n equals and greater or equal than 4, K they prove it for any subfield of the complex number, and for n greater or equal than 5 for any infinite field. So the strategy of their paper, or the main object of the paper, is actually they construct an invariant for birational map, which they call motivic invariant. So it's defined as follows: given any birational map from X to Y, they associate this birational map to an invariant C, which is the difference between the sum of EI and FJ, where EI runs over the exceptional divisor of phi, and FJ runs over the exceptional divisor of the inverse, phi inverse. And here this invariant takes value in the so-called Burnside group, but in this context, it's simply the Z module of birational isomorphism classes of varieties of dimension n minus 1 over k, because they're divisors. We assume X and Y have dimension n. So what this map does is it takes a birational map and it takes the difference of the birational type of the exception divisor. So this is a very natural object, and it's defined for any birational map over any field, in fact. So, and they prove in the most general setting, this C invariant is a group point homomorphism, meaning the C invariant of a composition of the maps are just the sum of the C invariant of the two maps. And therefore, an easy corollary after this is the C invariant vanishes for all the pseudo-regularizable maps because they are conjugate to isomorphism in codimension 1. The C invariant of the elements is conjugated by will be cancelled, and if it's isomorphism in codimension 1, the C is obviously trivial. So our main result is okay. So then they use this invariant. They find birational transformation of projective spaces with non-trivial invariancy. Well, the map is not. In some sense, it already exists in the classical literature. They're not the first ones to find such maps, but I guess this invariant and the property is really novel to them. So our main result is a generalization of their result to this subgroup of the Cremona group. We show that in the following cases, the group of rational automorphism of Pn preserving omega n is not generated by pseudo-regularizable elements, and as a corollary is not simple. In the following two cases, first is the same as the Lin and Shinder's assumption, n greater is equal to 3, k are these fields. The second one is n greater equal than 4, and the field we instead of any subfield of C, here I just write k equals to C, because we need some. To prove this, we use some generality assumption and argument, which requires the field to be sufficiently large. So it doesn't work for any subfield. But in fact, I could replace k equals to C just by any uncountable subfield of C. But here, for simplicity, I just write k equals to C. So another version of our theorem, which is essentially just a restatement, is that under the same assumption, the same holds for the group of Cremona birational automorphisms of the toric log Calabi-Yau pair, Pn with the torus-invariant boundary, which is just the sum of coordinate hyperplanes. And we just refer to this pair as the standard toric pair because it's the toric pair on projective spaces. So here I just like to recall there's a correspondence between the Cremona birational map of log Calabi-Yau pair and also the birational maps preserving the corresponding volume form up to a scalar. So the idea of our proof is very simple. We wanted to construct a birational automorphism, which is volume preserving with non-trivial C invariant, using the same strategy as Lin and Shinder. So basically, what Lin and Shinder prove is they construct a map in the Cremona group with non-trivial invariant C, but a priori their map does not preserve the torus invariant boundary or the volume form. So our construction basically extend their map to a volume preserving map. So here I just like to briefly mention we also studied another invariant, the C invariant for birational not only for birational map but defined for birational maps preserving our volume form specifically. The idea is that the invariant should take into account the information of volume form as well, like how it changes in the birational map. But eventually we proved that the value of that invariant essentially coincides with the Lin and Shinder invariant, at least in the context of birational automorphism for log Calabi-Yau pairs. So yeah, I suppressed those things, but that's another subject in our paper. So here's some basic setup, just about log Calabi-Yau pair and pairs with volume forms. So we work with pairs with logarithmic volume forms, where X is smooth projective, dimension n over k, and we are given a volume form omega x, which is a rational volume form on X, such that it has poles of order at most 1. That's what logarithmic means. And also the polar divisor, just the divisor of the zeros minus the poles, has simple normal crossings. And the last condition we can actually always achieve by blowups, just birationally. And if we also assume that this divisor minus the polar divisor is reduced, then we got a very nice log Calabi-Yau pair, x dx, meaning the pair is log canonical and kx split dx is linear equivalent to 0. So here is the definition of volume preserving maps. So we're given two pairs with volume forms. It's volume preserving if the row preserves omega x and omega y. So here I'd just like to mention, because in many contexts for birational geometry, volume preserving is the same as Cremona birational for log Calabi-Yau pairs. But here, in many contexts, okay, I'll explain this later. So let's talk about, if we start with a log Calabi-Yau pair, we can similarly get a volume form, but it is unique up to scalar. such that the divisor of omega x plus dx is 0. And here's the definition of a Cremona map between two log Calabi-Yau pairs. So which is you take the log resolution and it preserves the canonical class. So what I wanted to say is the Cremona automorphism and volume preserving are almost the same thing, but not exactly the same thing in our context. If we start with a volume preserving map as we've defined, it induces a Cremona map on the corresponding log Calabi-Yau pairs. On the other hand, if you start with a log Cremona map, it will preserve the underlying volume form only up to a scalar, but not physically. So therefore, I think in many contexts in birational geometry, volume preserving and Cremona are the same thing. But here we slightly distinguish them. And yeah, to put this difference, we can write an exact sequence from the group of Cremona birational automorphism of X preserving volume preserving birational automorphism of X preserving omega X. Every such maps induces a birational automorphism of X, which is Cremona birational with respect to the boundary dx. However, there is an image, so this map might act on the volume form non-trivially. So there's an image to GL, the global section of X kicks to dx, and rho has a name. It's called the pseudo-canonical representation. So the image is often non-trivial. The easiest example is the standard Cremona evolution on Pn. It's Cremona birational with respect to the torus-invariant boundary, but acts on omega n by -1 to the n. So if n is odd, it's not considered volume preserving for us. But it's not a big deal. So here's a theorem by Fujino and Gano. There's a boundedness result on the image of rho. It's always finite. Therefore, to study this group and this group, they will only differ by a finite index. Well, yeah, the first one is a finite index subgroup up to the other. So
which one is the subgroup? The volume preserving?
Yeah, the subgroup is the volume preserving subgroup. Yeah.
Okay.
Yeah, Burr X omega X is volume preserving, and XDS is Cremona barrage. And we are, our result is on both of these two groups. So it works the same. I'll stop using laser. I think every time I press laser, it goes to the last page. Okay. Yeah, so but our result is on both of these two groups. It's the same. They are essentially the same. Okay, so here's another some of the general things about log Calabi-Yau pairs. There's a notion called the co-regularity, which is the dimension -1 minus the dimension of the dual complex. So in the easy situation where X is smooth, the X is simple normal crossing, this is just the minimal dimension of a stratum. And a stratum means any intersection of the components on the boundary. So here's the example. On P3, if D is an irreducible quartic surface, there's only one component, it's dimension 2, therefore the co-regularity is 2. So if D is a smooth cubic surface and a plane intersecting along a curve, it has co-regularity 1 because this curve is the minimal dimension, has the minimal dimension as a stratum. And of course, for the toric pair, you have 4 coordinate hyperplane. They intersect. The smallest one will be 0. Will be points, so 0 co-regularity. And this is the standard toric pair, which we are interested in. So there is a theorem by Dukov in last year. He proves that on P3, if we have a log Calabi-Yau pair with co-regularity 0, it's always Cremona birational to the standard toric pair. So we can always transform it into the toric boundary birationally. So his proof is explicit, constructive. He basically classified all the possible quartic surface. Well, it will be reducible, or including reducible one with co-regularity 0. And then for each of them, he constructed a birational map to the toric boundary. And the map he constructed is actually inspired some of our construction, as I will explain later. So here's a lemma where we can see it as an example we need. in P3, if we have a cubic surface with canonical singularity and a plane, if the intersection is 3 lines forming a triangle, or a line and a conic meeting at 2 points transversally, then the co-regularity of this pair is 0. Okay, so the pair should be S plus H, not intersect. And by the theorem by Ducat, we know this is Crepin equivalence to the toric pair. So that will be important to us, but it's a technical thing. So here is the last generality thing about log-Calabi-Yau pairs. Is that there's many evidence that the birational geometry of log-Calabi-Yau pair with large co-regularity should be very rigid. So a theorem by Araujo, Corti, and Maserenti showed that over complex number for P3 and a irreducible smooth quartic, a general irreducible smooth quartic surface, the Crepin birational automorphism group coincide with the automorphism of P3 preserving this quartic.
So what's the geometric meaning of this quartic?
It's the dimension of.
I see the number, but what does it measure?
It measures how far away it is away from the toric pair. Yeah, but being 0 basically means it's toric pair. But it's not proved in any dimension. Only 3 by Ducat. Yeah. So it's a notion invented by Moraga. Yes. So yeah, they also studied when singularity appears. I think A1 and A2. And the appearance of singularity enriches the birational geometry of the pair significantly. It makes the group much larger. And in our case, we consider the other extreme side, which is the toric pairs with co-regularity 0. And we show basically our result is showing this group is very large and very pliable, so it has an opposite behavior as expected. So okay, now I could talk about our main construction. So I'd like to start with dimension 4 first, because it's a bit more interesting. So, but here we will work over complex number essentially. So here's the construction. The construction of birational map is essentially due to Hassan and Lai. So they consider a K3 surface of degree 12, RL, with polarization gamma, and this K3 is embedded in P7. So you pick up 3 general points on the K3, you project from it, you get a non-normal surface in P4 with 3 transversal level points, P1, P2, P3. And this SL non-normal surface in P4 is cut off by quartic. The linear system of the quartic contained in it has dimension 4, give rise to a birational map in the Cremona 4 from P4 to P4. So what this map does is it blows up the surface SL and it contracts some divisor to another surface SM, where SM is obtained in the same way from a projection from another K3 of degree 12. So you have another K3 of degree 12, you pick 3 points. You can realize SM as the projection of another K3 from 3 points. And in fact, the 2 K3 appearing on each side is are Fourier-Mukai partner to each other. So they have, and to compute the C invariant, in this case, it's very easy to see. The exceptional are just SL and SM. Well, the normal bond of SL and SM. So the birational type is SL times P1 minus SM times P1. Now, the main theorem by Hassan and Lai is for general SL arising from this construction, the Picard group is generated by the polarization, and the 2 surfaces are not isomorphic to each other, but derive equivalent to each other. So there's a very nice symmetry put together into this diagram, and they show that they're not isomorphic, but derive equivalent. And therefore, when the K3s are not isomorphic, they're not stably birational to each other, and the C invariant will be non-trivial. And that's essentially what Lin and Shinder used to prove the Cremona group in dimension greater than 4 are not generated by pseudo-regularizable elements, because there is this map with non-trivial invariancy. So here's a sketch of their proof. Basically, they construct a very explicit example, and in this case, they compute the middle cohomology of these two things, and they realize the translated lattice of the K3 as a sublattice of H4, and then they show they are isometry, and therefore they are derived equivalent. But we're not using the derived equivalence of these two K3 directly, but somehow the proof is quite important to us because that deals with a lot of the intersection theory, which is useful for us. So here is just a list of the generators of the algebraic part of H4, which they computed. It's generated by the pullback of general hypersection on P4 and L squared, and also gamma L tilde, which comes from the polarization essentially. It's the pre-image in X. X is the common resolution of the image in P4 of the polarization, and also Qi, which is the quadratic surface in X above the singular points, Pi.
So what is the torus-invariant invariant that distinguishes
Distinctly, they're not isomorphic.
Yeah, it is correct.
Yeah, I think correct.
Yeah, but what distinguishes?
Not
in H2.
is. They show when a Picard group is Z, they're not isomorphic.
And the degree be different. Degree of generator.
I think it's the is it? Yeah, I'm not. I don't really know it well, but is the Fourier-Mackay partner not isomorphic to it necessarily using the degree 12? I think
it's rather clear. So there are finitely many which guess.
I think yeah, degree 12
the
is
same derived category, but
okay.
theoretically. So
Yeah, I forget exactly the proof, but
yes, that's fine.
since it's degree 12, I think there's a unique non-isomorphic Fourier-Mackay partner, and they are these two guys. Yeah, I don't really know these things. Yeah, and so it has FQIs and also Fi tilde, which is the pre-image of the minus curve, one curve in SL, which arises from the projection, it's the exceptional curve above the points to project. So, and also the same set of objects coming from this K3 from the other side. So, and yeah, they also computed the intersection matrix and everything in it, which we use later. Okay, so now our main goal is just to extend this birational automorphism of P4 to a volume preserving map, or more geometrically, a Kraken birational map of toric pairs. So we want to find boundary divisor, which just phi extends to a Kraken birational map, and in addition to that, we need our boundary to be Kraken birational to the toric ones. So here's what we did. So we pick singular points from each of the surface on each of the side. We consider the quadratic surface in X above them, and we show that the image of the two quadratic surfaces in X remains to be quadratic surface in P4, and therefore they span P3, and then we let HL and HM be two P3. So, and on the other, then we just take the strict transform of HL and HM, which are singular quartic threefold. And this is how we constructed the boundary. So here's some interesting observation from our construction. So first is, these are using exactly the intersection theory and the computation by Hassan Lai. So we show that the image of K1 and Q1 are quadratic surface in P3, in P4, therefore they span P3. That's how we chose HL and HM. And moreover, so there's a typo. It's not HL. It's BL and BM has multiplicity at P1 and P2. So the two quartic surface we ended up with has multiplicity 3 at the point we started with. Therefore, in particular, they're rational. And moreover, we computed the intersection of them, which decompose into three components. It's first is the span of the three singular points. The second is which is a P2, and second is the span of the exceptional line and also a P1, also the point P1, which is also a plane. And the last piece is the quadratic surface. So yeah, what I find interesting is that all those like additional pieces in the middle cohomology coming from the K3 shows up in this intersection in the strata. And these three components are fairly important to our further construction because these are essentially how we realize the toric intersection eventually. Yeah, we find the map explicitly later. And another thing I would like to say is just maybe how I will explain how we find this. So we didn't start like this. So initially we wanted to achieve this goal, but there's so if we wanted them to be we want to find pair which are well, not equivalent. We want to find pair where are Crepin birational to the toric pair, and therefore each component should be rational. When we have a linear system of quartic, we need to search for rational quartic. We look through many rationality of quartic. It could be singular, this and that, containing plane or lines, whatever. But then we realized the easiest rational quartic are those with multiplicity 3 points. Then we started to look for, and yeah, we look for quartic in that linear system cut out SL with a multiplicity 3 points. And well, the obvious candidate will be the point is the singular point we started with. And then we find that computationally, there's exactly one element in this linear system with multiplicity 3 at this point. So in other words, BL can be characterized as the unique quartic in the linear system cut out SL with multiplicity 3 points at D1. And that's that's in fact how we find this construction. But yeah, to put it on the paper, we do a reverse engineer and start with the other side first. But yeah, that's how we find the construction. And then, as I said, we just find explicit Crepin birational map, transforming these two pairs to the toric pair. The construction is partially inspired by Ducat's paper in dimension 3. It's in some sense it's a generalization of Key's construction in many cases into dimension 4. But all of these are done there explicitly. And therefore we find also we find the C invariant of this transformation is 0. It doesn't even have to be 0 because they are the same map. Therefore, when we do the composition, the C invariant will cancel out anyways. But the punchline is eventually we get a Crepin birational map of P4, preserving the torus invariant boundary, but it still have the C invariant of the two K3, and therefore that is non-trivial. So, and thus we achieve our goal. Okay, so that was the story of dimension 4. So now let's look at dimension 3. It's a little bit easier. Well, actually, the construction seems more complicated, but the geometry is much clearer. So here we need the center of the blob to be a quintic genus 1 curve. Classically, this is realized. It's known that this is our intersection of Riemann 2,5 with P4. And C is cut off by quadric in P4, by quadric. So it's the base locus of the linear system of quadric passing through it. And this also gives a map so if we pick Q to be a general member in M, which is a smooth quadric threefold, so the linear system M gives rise to a birational map phi with this resolution. So phi blows up C in the quadric threefold Q and blow down another divisor to C prime, which is isomorphic to the degree 2 line bundles on C over K. And this is also quintic genus 1 curve. So again, if we want to compute the invariant C, this is just C times P1 minus C prime times P1. So now the point is, over algebraically closed field, these two curves are isomorphic, and the C invariant will vanishes. But Lin and Shinder, they show that under their assumption on K, those just assumptions of number field, function field of number field, blah blah blah. Under those fields, there exist such curves C with no rational points and also not isomorphic to C prime. So, and in particular, this will not happen over C, over a complex number. Therefore, their result that the Cremona group is not generated by pseudo-regularizable elements is still open in dimension 3 over complex numbers. So yeah, and over complex number, they also showed the C invariant for any birational map is 0 because birational geometry is controlled by the intermediate Jacobian in dimension 3, and over algebraic closed field there's plurality for even elliptic curve. Therefore, you can never have such behavior.
So why should prime becomes
This is a very classical link.
We see the
oversee?
isomorph.
Yeah, when they have a
Yeah.
point, they're isomorphic.
Yeah, but I mean, I couldn't see why it's become Picard. It's Picard too, right? Picard.
Yeah.
What's the question?
I mean, degree. I mean,
And it's probably why it's isomorphic to degree 2 line bound. It's
Because the map which goes this way contracts seconds of the curve. So the another curve basically given by 2 points.
Yeah, this is a quite classical map. We found it in a book in 1920 or something. Explain the geometry. Yeah, but it's quite interesting. Okay, then same goal. We want to find an anti-canonical divisor on the two sides, such that phi extends to a Cremona birational map. So now this is our construction in this case. So we pick a general plane H2 in P3 on the right side. Then we put Q1 to be its strict transform, which becomes a the parallel surface of degree 4. And if we choose Q, the quadric for generally, this dp4 is also smooth. Phi is given by quadric, the map. So Q1 is the intersection of two quadrics, therefore dp4, p4. P4. So now the C prime is a quintet curve, so it intersects H2. Yeah, also H2 is general, so they intersect at 5 points. That we can let R be the conic in the plane passing through these 5 points. Its strict transform under phi inverse will be a line in the parallel surface degree 4. Then we pick a general point on the line. We consider H1 to be the tangent hyperplane section of the quadric threefold at Q. Therefore, H1 is a quadricone. And we put S1 to be the strict transform of H1 under phi. But this point Q is chosen generally as away from the base locus. Therefore, S1 is a cubic surface, but with one A1 singularities. So here is the summary of the boundary. So on the quadric threefold, we find the boundary as a dp4 and also q1 and also a quadricone h1. And then we computed their intersection. It's a twisted cubic and a line intersecting at 2 points in the quadricone. So one of the point is the vertex of the plane h1, the quadricone h1, and the other one, it should be a smooth point on h1. On the other side, we have P3 and the plane H2, also a A1 cubic surface S1. So their intersection is a conic and a line intersecting 2 points. And as I've mentioned before, we already see on the right side, this is a toric pair by Ducat's result. Ducat's paper works over algebraic and closed field, but we verified those construction in our specific case exists over non-closed field as well. Or exists over the specific field we are looking at. Now we want to transform the left side to something nice. So we have the smooth point Q on H1. We project from it. Then we map the quadric threefold to a P3. The parallel surface degree 4 to a degree 3, which is a cubic. And also, it's a singular cubic because the point we project from lies on one of the exceptional line on the dp4. And the plane, the quadricone, since we project from a smooth point, it becomes a plane. Therefore, we get a similar configuration of P3, a cubic surface with singularity, and H3. And again, we can show that their intersection is a conic and a line intersecting at 2 points. Therefore, we just basically put this construction into symmetries. We have the same configuration on each side, and again, by Ducat's result and after verification that the construction exists over the field we're working with, we find that Cremona birational map of these two pairs to P3 with the torus boundary, such that the map eventually has non-trivial invariancy. So maybe I should just briefly explain how we find this construction. So this is inspired by equivariant geometry. So in particular, we can make this map C5 equivariant. So how did we start to choose these hyperplane sections, basically? The H2 and Q and H1 is that we could put a C5 action, the cyclic group of order 5, on a quintic genus 1 curve. So the way to do this is we started with C5, pick 5 different characters, you pick a 5-dimensional representation with 5 different characters, then it induces an action over Riemann 2-5. You find an invariant P4, then you intersect, you get a quintic genus 1 curve with C5 action on it. Then you can extend this action on to the cubic threefold and P3. You can have an equivariant birational map phi. Then we are looking for invariant hyperplane section and just invariant divisor. Then it becomes clear because over non-closed field there are infinitely many hyperplane sections. But when you have a group action, usually you have very few invariant hyperplane sections. So the candidates are very few. We've tested a few of them. Most of them are very bad. But there's one which works, which is this thing. And then we recovered this construction without symmetries. But in particular, we can make these whole diagram C5 equivariant when the group is in presence. But it's not too relevant to us. Okay, that's all I want to talk. Thank you.